Let's analyze the aerodynamics of an Earthmover. This would typically consist of dropping a massed object in the air until it reaches equilibrium. This would allow us to find the drag coefficient. Trouble is, the Earthmover's mass is unknown. Assuming all information in the previous video is true, we have multiple methods to work with. Alright, fine, just get the density of typical materials that make the Earthmover and approximate from there. However, I feel like that would be more inconvenient than challenging, and worse, it would be imprecise. We have several means to calculate the mass of an Earthmover, as imaged. The problem with momentum is we don't have an object of similar mass to the Earthmover. Furthermore, I believe spawning the Earthmover using a rocket launcher would just give the Earthmover properties of a rocket. Using moments would just require a stable pivot, which isn't that easy to achieve. Obviously, you can calculate the mass of the sun using its gravitational field strength, but the Earthmover is unfortunately not a celestial body. Restitution was a great idea, but is independent of mass. I instead tried to calculate the drag coefficient using SimScale. That failed too. It doesn't like models with overlapping phases. So there you go. Calculating the drag coefficient or mass of an Earthmover is hard. Instead we'll be testing how the Earthmover copes with resonance from wind. This one is actually possible. See, resonance is an occurrence wherein if a force is applied at a specific time period, the object would slowly increase amplitude. This is bad. So some towers use mass dampers to absorb force by the wind. We'll model the Earthmover's brain as a damper, since it's a pendulum. That assumes that alongside the force due to wind, air resistance, gravity, and elasticity acts on the brain. And we get this differential equation, which, like the last one, probably looks extremely complicated to someone who hasn't done them. But for those that have, it looks even more complicated. See that v squared? That would be fine if x wasn't there. Further, there's a sign. Obviously, you can just ignore the v squared term since it's so negligible and approximate sine x as x. But I would never resort to such methods such as small angle approximations. Surely you can use the RKF45 method to numerically solve the equation, but that would require us to have all constants. Area and length of the pendulum are easy to calculate. I'll also use the differential equation in terms of theta. After painstakingly going through 43 fucking frames to calculate the angular displacement of the pendulum, I also got the time period of its oscillations. But what does that leave us with? Mass and drag coefficient again. First of all, fuck that, I'm not gonna try to solve the mass again. We'll just assume that the drag coefficient of the brain is of a cube. Second of all, we lack the spring constant of the brain, which really sucks. Fortunately, there's some very important information in an ultrakill dev stream that would make this much easier.
The belly jiggle physics.
Oh yeah, the cobalt care jiggle.
Yeah, it's from Cobalt Care.
Yeah, it's a boob jiggle physics from a porn game, and we put it on the belly of the Minotaur.
Oh, on the brain, which we can talk all about when we get there.
I was initially anticipating this to be a funny part, but holy shit, finding the number took ages. But at least we got the damping constant for our troubles. But no thanks, I don't believe in lies such as the drag's non-existent direct proportionality with velocity. We could also use the density of breast to calculate the mass of an Earthmover's brain, but I feel like that's cheating. His brain literally has metal, which means unfortunately we do have to use small angle approximations to estimate the mass. Solving the quadratic equation for this approximate defect, the imaginary part is the angular frequency, so you can use this equation to solve the mass of the brain. Fortunately, it comes out at a realistic value. Next, we insert this into our original defect and solve it using the RKF45 method, which gets us this function for angular displacement per unit time. We can very easily deduce the frequency of the pendulum, but let's find the natural frequency of the Earthmover. Assuming the Earthmover is a cylinder, for some reason, we can model him as a string. Fortunately, since the tension would be gravity, his mass is unnecessary. This results in a natural frequency a third of the frequency of the brain's pendulum, which means it's probably doing a great job at keeping Benjamin from resonating in the wind. Not much flaws in this one compared to the last one, but it certainly used a lot more assumptions. Given the large surface area of Benjamin and his thermal velocity likely being slightly faster than V1's, Earthmover would definitely have a realistic mass. Next video I'll probably calculate the power of the agreed sun or something by estimating the temperature of the SAD, but now I think about it, that sounds like it would need even more approximations, and I probably won't have any opportunities to have a differential equation in there.